Hi everybody. I wanted to give this quick getting started video for Project 1B. First thing I want to say is you should really understand A-lists from Lecture. They are closely related to array decks. One possible exercise, if you want, is to open up this getting started file and fill in the blanks in the A-list method. And when you're ready, you can look at the solutions, which are available also on the GitHub repo. So you might find that a fun exercise just to get the basics. You can probably knock it out, and if you know the lecture, in 10-15 minutes, and it's a good baseline for finishing the rest. Now, once you've gotten a solid understanding of A-list, the next thing I want to say is that there's a little bit of planning for this project. So unlike Project 1A, where we told you, hey, you should really use a circular sentinel, but you can do these other couple things, here we're leaving things a little more vague. We still want you to use a circular approach, but we're a little vague about what it looks like exactly because we want you to explore the territory. Okay? So I have some slides that follow this. I'm going to talk through that give you some tips, but the key thing is that you have to come up with the design. It has to take into account resizing, and I think it's fine to work with other people to talk about your high-level design. I would really recommend working out some examples on paper. Start with an array size of 8, and just make sure you know how your data structure is supposed to work. Some of you on Project 0 might have had the experience of having some vague idea and then writing code to implement that idea, but the thing you were trying to build wasn't actually useful. I saw that a lot in office hours, actually. So what I really want you to do is make sure you have a solid idea, and then, only then, start writing some code. Now, one warning is we don't want you to come up with a design and sit down with other people and write code and say like, hey, how'd you do add first? Oh, when I'm doing add last, how did you do that? Because your code's going to converge and be too close. We want you to really write your own code, even if you have roughly the same idea design-wise. We'll get to doing more detailed work in terms of partnerships in Project 2B. For now, we really want you to try and do things independently. So I'm going to give you a bit of possible design, just to kind of float what one might do. You don't have to use this design. I've seen people do this totally different. I've seen people do the problem without a circular array and have it be fast. But here's a possible design that you can use as a starting point, and you can adapt this and use something just like this for the project. So my project, when I implemented it, my array deck had 4 variables. I had a size, a next first, a next last, and an items field, or also known as an instance variable. And items here pointed at some array of length 8 initially. And quick note, as it says on the slide, items is not pointing at element 3, it's just pointing at the entire array. That's just how the figure looks. And so conceptually, when someone adds A, what we expect is that the deck goes from having nothing to having A. When you add last B, we have B on the end. When we add add first C, C goes to the front. When I add last D, I end up with C, A, B, D. Now this is what I call the cave dwellers view of the universe. This is what the deck is conceptually. But if we look at what was happening, that the monks, if you haven't watched lecture, you probably have no idea what I'm talking about. But the monks, this is what they're perceiving, that there's these 4 variables being manipulated in this way. So let me do that again real quick and show you that when I add A, what happens is, because I said add last A, the next last is in position 5, and that's where it went. Now if I add last B, it's going to end up in position 6 because next last is 6. Then if I add first C, well, next first used to be 4, that's where the C goes, and so forth. So I can keep adding, and you can follow along in these slides and make sure that it all makes sense. So after I do add last G, add last H, and I just follow that pattern, and by the way, it might be a good idea to stop this video and make sure you can step through the slides. They're linked on the spec, and make sure that everything makes sense. And then when I want to finally add G and H, what I end up with is this: E, G, H, F, C, A, B, D. The size is 8, next first is 2, next last is 3. Okay. So obviously now, after the next add last operation, we're going to need a bigger array, right? So the array, if we want to add another item, like let's say I, it would need to go in between the H and the F somehow. And so how you do that, I'll give you some possibilities, and you're free to pick whichever one you like best, okay? Before I do that, I want to note something, which is that this array right here, E, G, H, F, C, A, B, D, represents the deck F, C, A, B, D, E, G, H. You might ask, why isn't F in position 0? Well, keep in mind that when the deck is first having items added to it, we don't know if we're going to say add last or add first. So, it doesn't really make sense to try and force the array to be F, C, A, B, D, E, G, H. You'll see that it evolves over time, that as you add items, it fills in. Okay. All right, so back to that question of how we deal with resizing. So when we want to resize the array, what we're going to do is make a bigger array and then copy all this data over. So let's say we're adding last z. Before we add last z, we have E, G, H, F, C, A, B, D. And afterwards, any of the following three things would be perfectly reasonable approaches. We could, for example, have E, G, H as these items here, then Z, and then F, C, A, B, D, right, at the very end. And so if we think about this array here, if we read it off, apparently the front is F, then C, then A, then B, then D, then E, then G, then H, then Z, okay, which matches the same order, and the F happens to be at this position 5 from the end. Okay, totally arbitrary choice. We could also represent it as F, C, A, B, D, E, G, H, Z, where F is at the front, or F could be here. Point being, any of these are totally valid. They're all fine. Okay. And the reason this is okay is, again, this allegory of the cave. This old slide here, this is the cave dwellers versus the users of the data structure. So the underlying representation could be anything at all. I think these are the three most natural representations, and it's supposed to represent this conceptual idea. You can also do something totally different if you want, as long as it is fast. The key thing is that your add first and add last operations need to be constant time, except when we have a resize. Okay, so you can't be sliding everything over. That'll be too slow. So one last tip is you don't have to use array copy if a for loop is easier. So for example, if you wanted to use array copy with this top approach, or actually any of these approaches, you might find yourself needing to make 2 or, I don't know, 3 array copy operations somewhere in your code. I personally don't like using array copy. It will result in somewhat faster code, but it's not going to make a difference to the autograder, and I think it's harder to think about. So I generally recommend not using array copy. Okay. All right. Now that we've got our sort of design tips, I have one last thing to talk about, which are general tips. So I think it's really important to take things just a bit at a time. If you try and write the entire ArrayDeck class all at once, it's going to be terrible. It's just so hard to debug. You have no idea what's happening. You really want to be following the test as I go approach, where you write a toList function and you validate the individual pieces. We really tried to force you into doing that in linked list deck. ArrayDeck would give you a little more flexibility, but I hope we convinced you in linked list deck that incrementally testing each piece as you go is the better way to go. If you find that you've written too much stuff and you're overwhelmed, maybe comment out all the methods except for, say, add first and add last and toList. See if you can figure out what's going on then. Then you can reveal your other methods that maybe you shouldn't have started playing around with yet. Now, if your first try goes really badly, maybe take a breather, take a day off, depending on if you have time relative to the deadline. Maybe scrap your code and start over. The hard part is coming up with the design. The easier part is writing the code. Once you have a clear idea of what you're trying to do, writing the code is less challenging. And it may be that the original design you come up with is so complicated that it's basically useless. That's happened to me many times. It can feel bad to throw away code that you wrote, but realize that most of the work was happening in your head, not on your keyboard. My solution, just for example, is 112 lines, and that includes all the comments, the white space, the brackets, and the helper functions. And I have a few helper functions. You might think of what those might want to be. Lastly, one thing that's a little tricky is the resize operation. So one thing you might consider doing is don't resize at all until you know your code is working pretty well without resizing. Now, obviously, you need to resize in order to get full credit. But at first, what you could do, a workaround, is just make the array really big. Make it 10 million items big, and that'll convince you that it's plenty fast and it works correctly. Then you'll lose resizing, so you're not wasting a bunch of space. I have to reiterate, I think it's hard to write code that uses array copy, so only use array copy if you really want to go through the exercise of using array copy. Lastly, my resize method, there's no reason you can't use other methods inside of a method you're writing. So for example, you might find the get method useful in your resize method. Maybe, maybe not, but I'll just mention that my resize method uses get. It feels pretty good. Okay, that said, that's all I got to say about Project WIMP. I hope you enjoy it. Yeah, have a good project time.